Okay. Till now we have discussed about the basic part of ideal filters, and we have also seen its frequency characteristics, and we also said that ideal filters are not realizable in practical cases, right? So today we'll get an introduction of filter from analog to digital. So that will remove most of our doubts, how it come into the existence, what are its practical uses, how we can use it as a practical part. We can see those important aspects one by one. So today's topic is an introduction of filter from analog to digital, right? So we'll go through this particular topic very quickly and we'll cover the most important aspects, right? So before starting, we are assuming something things. First is we are doing this analysis for low pass filter, that is LPF, right? So if you want to design an LPF using RC filter, RC circuit, so we will use RC circuit to implement LPF. Right? So we have an input signal that is say as Vt, and then we have a resistance R, and then we have a capacitance C, right? And the output we have obtained across this capacitance C, that is V0 of T. Okay. So first part is we know the characteristics of C, that is for IV characteristic of C, it is I is equal to C dV by dt. And if we take a Laplace transform of this relation, that is it is of IT and Vt, so it is I of S is equal to Cs V of S minus V0. This V0 is the initial condition and we are assuming it to be 0. So Is is equal to Cs into Vs, and by arranging in Ohm's law, it is Vs is equal to Is over Cs, right? Then we can redraw this particular circuit in terms of Laplace transform. So it is Vs, and then there is a resistance R, then there is a capacitance which can be written as, in resistive form it is 1 by Cs. So resistance is 1 by Cs, and the output is obtained is plus minus V0 S. Then the transfer function H of S is nothing but equal to V0 S over Vs. V0 S we have already obtained. We know that it is Is over Cs. Is is the current going across this loop, so it is Is by Cs. Now we have to find out Vs. So Vs we knew it is Vs minus Is into R minus V0S by Cs. Sorry, it's not V0S, it is I of S equals to 0, right? So then Vs will be equal to Is R plus 1 by Cs. So we can write it like this: Is R plus 1 by Cs. This Is will be cancelled out, so it will be 1 over 1 plus RCS. Now we know certain part, that is RC is the time constant. Time constant of the circuit, and we can equate to tau, and tau is equal to omega naught, that is we can write it like omega naught in frequency domain, that is 1 by tau. So if we can substitute this particular relation, so our Hs will be equal to 1 over 1 plus S by omega naught, and for we know S is equal to sigma plus j omega, and for the case of Fourier transform, sigma will be equal to 0, so H of omega will be equal to 1 over 1 plus j omega over omega. Now we have obtained this transfer function in terms of frequencies, and we knew it's a low pass filter. We will plot it and we will see that also. But first we want to find out its magnitude, right? Because from magnitude we will find out it is a low pass filter or not. So to find out the magnitude, we have to do one thing. We will multiply with 1 minus j omega by omega naught over 1 minus j omega by omega naught. So it will lead to 1 minus j of omega by omega naught over 1 plus omega by omega naught square. So mod of h omega is equal to 1 over 1 plus omega by omega naught square root 1 plus omega by omega naught square. Okay. And this will come out to be 1 over 1 plus omega by omega naught square. Now if you want to plot this particular characteristics, that is mod of h omega against the value of omega, right? So we'll know when omega is equal to 0. When omega is equal to 0, h omega will be equal to 1. As omega increases, the ratio h omega will keep on decreasing. So it will decrease like this. Goes like this. And there will be some point when the frequency omega will be equal to omega naught. There will be some point. Right? We want to find out what happens. Now h omega, mod of h omega, when omega is equal to omega naught, will be equal to 1 over under root 1 plus 1, that is equal to 1 by root 2. And at that particular point, our magnitude is equal to 1 by root 2. Now why is this magnitude is important? We will just see this particular part. Generally this particular curve is plotted in decibels. So if you find out the decibel value, so mod of h omega, which is equal to omega equals to omega naught equals to 1 by root 2, and if you find out it in dB, it is 20 log base 10 mod of h omega for omega is equal to omega naught will be equal to 20 base log 10 2 to the power minus 1 by 2, and this will equal to minus 10 of log 10 to the power 2. And if you find out the log 10 to the power 2, it is equal to minus of 0.301. So it will be nearly equal to minus 3 dB. So what this magnitude signifies that the maximum magnitude of this filter deteriorates 3 dB at this particular frequency, that is equal to omega naught. So this particular frequency we usually call it as cutoff frequency. This particular frequency, omega naught, and the magnitude at this particular point we took it to 1 by root, right? So it is not always required that the cutoff frequency to be 1 by root, that is at omega naught. It is dependent upon your application. If you want to have a kind of application which requires very high magnitude, so you can make your cutoff frequency at around 0.01 at 0.1 dB or 1 dB or 2 dB. It is not required. You can go up to 3 dB, right? But in general, most of the bandwidth parameters and most of the generalized characteristics go with the cutoff frequency of 3 dB. So we have explained this particular part, that taking your cutoff frequency at 3 dB. Now another important aspect with this particular relation is the phase part. Okay, we have this H omega equals to 1 minus j omega over omega naught, 1 plus omega by omega naught square. So then we can find out the phase. Phase we can say it as phi of omega, p of omega, that is tan inverse imaginary part over real part. So at imaginary part and real part both constitute this denominator, so it will be cancelled out. So our result will be for phi omega will equal to tan inverse minus of omega by omega. So if we plot this particular relation, right, just we plot the part magnitude part, we can see there is a negative sign, it will come outside, so phase is negative, so we'll plot it in negative direction, that is with omega, and it is phi of omega. So one can see when omega is equal to 0, phase is also 0. Phase is also 0. Now as omega increases, phase also increases, right? Keeps on increasing and goes up to maximum value of pi by 2 when omega tends to infinity. And when omega is equal to omega naught, at that particular point omega naught is equal to, phase will be equal to pi by 4. That is minus of pi by 4, and then it is minus of pi, right? So we have obtained the analog filter characteristics. Now we want to look for the digital filter characteristics. So to find out the digital filter characteristics, we have to go through again the same transfer function, that is Hs is equal to 1 over 1 plus S into Rc, right? So we can write it like this. So we can take 1 by Rc common, so it will be 1 over 1 by Rc plus S. Now we want to find out the value of H t. For that we have to find out the inverse Laplace transform of this Hs, and we want to use our knowledge of Laplace transforms. So we will find out from that, let xt is equal to a e to the power minus at into ut. Then to find out xs, we'll integrate from minus infinity to infinity a e to the power minus at ut e to the power minus of st dt. Now a will go outside and our integral will go from 0 to infinity due to this ut. So it will be a minus a plus s t dt, right? Then we can integrate to find out a over a plus s with a negative sign. Then e to the power minus a plus s t 0 to infinity, and it will be equal to a over a plus s, right? So if we compare this relation a over a plus s with 1 by rc, 1 over 1 by rc plus s, we can find out that ht is nothing but equal to 1 by rc e to the power minus t by rc ut, right? So we have find out this particular ht using the comparison with this xt and find out the value of ht. Now to find out digital filter design, we have to sample ht, and let the sampling frequency is fs, then t is equal to 1 by fs, and there are n samples, so t will be equal to nt. So after this ht will be equal to h nt, also written as h of n, go through, it will not equal to, it will go through this sampler and this result will come, and equal, it will come out to be 1 by rc exponential minus nt rc u nt. Now we have find out the value of hn, and now we want to find out its z transform. So we will find out the value of hz, that is n equals to minus infinity to infinity 1 by rc exponential minus nt by rc, and then it is unt. Now due to this unt, our transform will be n equals to 0 to infinity, 1 by rc will come out of this summation, and it will be minus into z to the power minus n will be there, sorry. So it is minus t by rc z to the power minus 1 to the power n, right? Now this particular series is nothing but a GP series. This is a GP series, and it will converge only if e to the power minus t by rc z to the power minus 1 should be less than 1, and for that particular case hz will be equal to 1 by rc 1 over 1 minus e to the power minus t by rc z minus 1, right? For an infinite geometric series which converges, its sum will be equal to 1 over 1 minus e to the power minus t by rc into z to the power minus 1, right? Now to make a filter, we have to optimize the gain of the filter, right? So we want during a pass band its gain will be equal to 1, and at stop band its gain will be minimum or 0. In general we want 0, but its gain should be optimized at the pass band, and we want to set it equal to 1. To set that, we will substitute this hz for z equals to 1, and we will multiply this particular term with a arbitrary optimization constant, and we'll write it like a dot 1 by RC over 1 minus e to the power minus t by RC, and that will be equal to 1. Then it is optimized, right? We want to find out the value of A. So A is equal to RC 1 minus e to the power minus t by RC. Then our optimized HZ, we'll write it again as HZ, will be equal to RC will be cancelled out. It will be 1 minus e to the power minus t by RC over 1 minus e to the power minus t by RC Z inverse. Now this transfer function is optimized, and let's say e to the power minus t by RC is, as it is a constant, it depends upon the sampling frequency and value of R and C, we substitute as alpha. So if we substitute the value of alpha for e to the power minus t by RC, our HZ will look like 1 minus alpha over 1 minus alpha into Z inverse. Now we want to find out a difference equation, because that is an important point, we want to do it. So HZ can be written as YZ by XZ, and it is equal to SZ, and that is equal to 1 minus alpha over 1 minus alpha Z inverse, and then it is YZ minus YZ alpha Z inverse equal to XZ minus alpha XZ. So if we take inverse of Z transform, then Yn minus alpha Yn minus 1 is equal to x of n minus alpha into x of n, right? So one can write it like this: Yn is equal to xn plus alpha Yn minus 1 minus of xn. Now we also want to realize this particular system. So it will be, we have an input signal xn, right, and we obtained an output signal yn, right? So we have obtained input, so we have an input signal, we have obtained an output signal yn. Then there is a delay element, that is Z inverse, right? And then there is this xn multiplied with minus of 1 coming together both, and adding at this particular point, there is a summation at this particular point, and going back again with multiplication of alpha. So we multiplied alpha at this particular point, and there is a summation at this particular point. So I mark summation with this. There is summation at this particular point, there is a summation at this particular point, and there is multiplication of minus 1 here, alpha, and we have realized this particular RC circuit from which we have started, now in digital format. Now again we want to find out the magnitude and the phase response of the filter, which we have find out in digital domain. H of Z is equal to 1 minus alpha over 1 minus alpha Z inverse. Now the ROC of this particular system is 1 minus alpha Z inverse equal to 1, that is Z is equal to alpha. That means ROC is mod Z greater than alpha. Now we knew from a full Z transform characteristics, if we have a unit circle like this, right? So it is the exponent Z mod Z equals to 1 equals to e to the power j omega mod. So the Fourier transform will only exist over this unit circle, right? Because there exponential j omega is defined. For all other part, exponential j omega is not defined. So what does it mean? That if you want to find out the frequency response of any system, and if it does not involve this unit circle, then its frequency domain representation cannot be find out. Then their exponential j omega is not valid, and that for that particular function, the frequency response we cannot find out the Fourier transform, right? So that to satisfy this particular case, this alpha should be less than 1, and we know alpha is what? Exponential minus t by rc, right? And it should be less than 1. So this condition should be satisfied. That's mean this alpha value will lie somewhere here, wherever, but it will inside this particular unit circle. And if some pole lies outside this unit circle, then ROC will not involve this unit circle, and for that particular case, that filter will be unstable and it will not involve. Then it is impossible to find out its Fourier transform. So for an filter, it is always mandatory that all the poles of that particular filter should reside inside the unit circle. Then only you can find out this exponential j omega, which is its Fourier transform. Then you can only realize its frequency domain analysis when all the poles are inside this unit circle, right? That means ROCs will involve that. For this particular case, if this is the case, then ROCs will involve this unit circle, and this exponential j omega is valid, right? Now we can find out the value of h omega by substituting z is equal to e to the power j omega, right? And then h omega will be equal to 1 minus alpha e to the power minus j omega, and that can be written as 1 minus alpha over 1 minus alpha cos omega minus j of sine omega. We can write it like this, and then this equation can be further solved. Minus alpha with 1 minus alpha cos of omega minus alpha j sine omega. Now we want to analyze its magnitude and its phase. So that for that particular case, we will multiply this particular equation with 1 minus alpha cos of omega plus alpha j sine omega with 1 minus alpha cos omega plus alpha j sine omega, which leads to 1 minus alpha cos of omega plus j alpha sine omega over 1 minus alpha cos omega square plus alpha square sine square omega. Right? So it is 1 minus alpha and 1 minus alpha cos of omega plus j alpha sine omega to 1 plus alpha square cos square omega plus sine square omega minus 2 alpha cos omega. So it is equal to 1 minus alpha cos omega plus j alpha sine omega, and then the solution will be 1 plus alpha square minus 2 alpha cos omega. Okay, This is nothing but h of omega. Now we want to find out the mod of h omega, that is equal to 1 minus alpha over 1 plus alpha square minus 2 alpha cos of omega under root 1 minus alpha cos omega square plus alpha square sin square omega. Solving this will lead to 1 minus alpha over under root 1 plus alpha square minus 2 alpha cos omega. Okay, so this is our magnitude. So, and we know alpha is equal to e to the power minus t by rc. So one can see the magnitude of the filter can be tweaked by varying the value of alpha. So if we vary the value of alpha, we can tweak the magnitude of the filter. That is very important property. So that's mean our magnitude of the filter is dependent upon alpha, and alpha can have a value from 0 to 1, right? Alpha cannot have a value higher than, so you can say it is mod alpha. Mod alpha should have a value from 0 to 1, right? So it should involve a unity circle within it. So if we substitute alpha is equal to 0, you can see it is 1 over under root 1 plus its h omega will be 1. For that, alpha is equal to 0 mod of h omega will be equal to, if we substitute alpha is equal to 0, so it's 0 0, so h omega is just equal to 1. So it is allowing all thing to be passed out. And we also see after some point that if alpha is possible or not, but right now it is possible. And if we substitute alpha is equal to 1 mod of h omega, you can see it is 1 minus 1 is equal to 0. So mod of h omega is equal to 0. So that's mean mod of h omega will have higher and higher values when alpha is tending towards 0, and it will have a minimum value when alpha will tend towards 1, right? So we can optimize this particular property by varying alpha from 0 to 1. Next is we want to find out the phase response of the filter, and we'll come back again at this particular point and we'll see, right? So we want to find out the phase, right? So it is phi of omega, that is equal to tan inverse imaginary part over real part. As one can see, the common part, that is 1 minus alpha, which will come at both sides, will be cancelled out, and then the denominator part will be also cancelled out. So only part which will remain is tan inverse. From imaginary part, it is sine alpha sine of omega, and from the real part it is 1 minus alpha cos of omega, right? So this is our phase of the filter. So we can see that this alpha, right, we can see this particular alpha can modify the phase of the filter. So as alpha goes to 0, so it's 0 by 0, so it's tan inverse 0, so your phase will be equal to 0. That's mean if alpha goes to 0, right, then phi of omega will be equal to tan inverse 0, that is equal to 0. And for alpha is equal to 1, it will be phi of omega will be equal to tan inverse sine omega over 1 minus cos of omega. Next, we are interested to find the cutoff frequency. So for that case we know mod of h omega will be equal to 1 by root 2 at the 3 dB frequency, right? And our magnitude, which we have already find out, so we'll see from that particular part, that is equal to 1 minus alpha over under root 1 plus alpha square minus 2 alpha cos omega, that will be omega c, right? So it is 1 minus of alpha over under root 1 plus alpha square minus 2 alpha cos of omega c. Okay, so this is for omega is equal to omega c. We want to find out the cutoff frequency. If we square both sides, that will be equal to 1 minus alpha square over 1 plus alpha square minus 2 alpha cos of omega c equals to 1 by 2. So it is 2 1 minus alpha square equals to 1 plus alpha square minus 2 alpha cos of omega c. So it is 2 minus 2 plus 2 alpha square minus 4 alpha equals to 1 plus alpha square minus 2 alpha cos of omega c. So cos of omega c will be equal to, that is minus 1, and then it is minus of alpha square, and then it is plus 4 alpha 1 by 2 alpha. So omega c is equal to cos inverse 2 minus 1 by 2 alpha minus 1 by 2, right? So one can clearly see at this particular point we cannot put alpha is equal to 0 at this particular point. If we substitute alpha is equal to 0, then this particular relation will go to infinity, and for that particular case omega c will does not exist. So alpha can tend towards infinity but cannot be infinity, so it cannot be a very high value. So one can find out the values of alpha by using the roots of this particular system. So we can find out the values of alpha which can satisfy this particular relation, and we can write it like this. It is equal to cos inverse, right? So it is 4 alpha minus alpha square minus 1 over 2 alpha. So it is cos inverse minus 1 by 2 alpha, right? And it is equal to alpha square plus 1. So it is plus 1 minus 4 alpha. So if we find out the root of this particular equation, alpha will be equal to 4 plus minus under root 12 by 2. Now we cannot have alpha greater than 1. So this is not possible. So this is not possible. So the only case which remains with us is that is alpha is 4 minus under root 12 by 2, and in this case alpha will be less than 1, and that is a true case. So we can find out the values alpha, and by setting this particular term we can modify further the values of RC and other constant to analyze the value of magnitude and phase of the filter. That's all for today. Thank you very much.